This is the first lecture for Text Unit 3, which introduces the idea of moles. Let's begin this discussion by noting something you already know. The masses of atoms and molecules is very small. For specific examples, specific numerical examples, the mass of a proton is 1.6 something times 10 to the negative 27 kilograms. An electron is much less massive than that. Its mass is only 9.1 times 10 to the negative 31 kilograms. A typical water molecule has a mass about an order of magnitude higher than the proton mass. It's about 2.99 times 10 to the negative 26 kilograms. These numbers are difficult to work with arithmetically. They're extremely tiny. It should be clear that there are many atoms or molecules in a macroscopic sample of a substance. Macroscopic is a word meaning big enough to see. Atomic mass units are useful units for the masses of tiny particles. Atomic mass units are defined by taking the mass of a carbon-12 atom, 6 protons and 6 neutrons, and defining it as exactly 12 atomic mass units, defined as AMU, or U. An atomic mass unit is equal to 1.660540 times 10 to the negative 27 kilograms. Provided with this equality, it's possible to make unit conversions from one of the unit to the other. So here I take the proton mass in kilograms, multiply that by a unit conversion factor with one atomic mass unit over 1.66 times 10 to the negative 27 kilograms. Kilograms cancel. And we find the mass of the proton is 1.0073 atomic mass units. This number is a lot easier to work with arithmetically than the number above expressed with scientific notation. No need to use scientific notation to express this number. Now, as chemists, we'll be interested in counting how many atoms or molecules there are in a substance, because chemistry happens by the atom or by the molecule. In the laboratory, we often weigh out amounts of substances in grams, however. What chemists need is a way to count molecules or atoms in a gram of substance. This is accomplished by defining 1 mole so that 1 mole of carbon atoms, carbon-12 atoms, equals exactly 12 grams. In other words, a mole is a number of stuff, whatever it is you're counting. And in this case, a mole of the carbon-12 atoms weighs 12 grams. The number that makes that work out is 6.022 times 10 to the 23rd, to 4 significant figures. So 6.022 times 10 to the 23rd carbon-12 atoms has a mass of 12 grams. With this definition of mole and atomic mass units, 1 mole of protons weighs 1.0073 grams. We just saw that 1 proton weighs 1.0073 atomic mass units. A mole weighs 1.0073 grams. In general, the mass of a particle in atomic mass units is the mass of a mole in grams. If you look at your periodic table handout, it will show you the mass of an average atom of each element in atomic mass units. Naturally, this is the equivalent of the mass of a mole of atoms in grams. So you can look at your periodic table, look in the box for carbon, and you'll find that a mass of a mole of carbon atoms weighs 12.011 grams. Alright, now this is an average mass of the carbon atoms. This average reflects the fact that carbon is not just carbon-12, but a mix of isotopes with mass numbers of 12, 13, and 14. So the average mass is a bit higher than exactly 12 because of these other isotopes. If you have molar masses for elements, you can find a mass for mole of any compound. So for a molecular compound, the molar mass is the sum of molar masses of the atoms in the molecule. Okay, so the molar mass of H2O is 2 hydrogen molar masses, 1.0079 plus 1.0079, plus 1 oxygen molar mass, 15.9994, or 18.0152. So a mole of water molecules has a mass of 18.0152 grams. Note just briefly, sig fig addition rules apply to finding molar masses. So here is an addition problem. Each of these numbers is precise to the 10,000th place. The answer is written to the 10,000th place. For an ionic compound, the molar mass is the sum of the molar masses of atoms in a formula unit. So, for example, consider the magnesium chloride molar mass. Molar mass of magnesium of one chlorine and another chlorine to the 100th place is 95.211 grams. So 95.211 grams is a mole of magnesium chloride, which means it's a mole of magnesium atoms and 2 moles of chlorine atoms. If you could find the mass of moles of elements of compounds, it's possible to perform stoichiometry. Stoichiometry in general is calculations with moles. Molar masses in particular allow conversions from grams to moles and moles to grams. Let me illustrate that with magnesium chloride. A mole of magnesium chloride, as we've just seen, has a mass of 95.211 grams. You can write that as an equality. 1 mole, 95.211 grams. Well, the 5 significant figures, this is an equality. Okay, suppose I have 10 grams of magnesium chloride. I'll put that here. I write that down here. I can convert a quantity like this to moles by multiplying it by a unit conversion factor assembled from this relation. In this case, mole goes in the numerator, and 95.211 grams goes in the denominator. Grams will cancel, and we'll leave units of moles, and the thing we are thinking about is magnesium chloride. So 10 grams of magnesium chloride is 0.015 moles of magnesium chloride. At this point, you should be able to find how many moles are in 65.2 milligrams of cesium nitrate, 0.115 grams of magnesium bromide, and 39.1 grams of sulfur dioxide. Stop the presentation and attempt this calculation before moving on and seeing the correct answers. First, let's consider the cesium nitrate, 65.2 milligrams. Molar masses relate moles to grams, so it's necessary to convert this quantity to grams. 65.2 milligrams multiplied by unit conversion factor from milligrams to grams gives 0.0652 grams. I can calculate the mass of cesium nitrate as 1 cesium mass 1 nitrogen mass, and 3 oxygen masses. Remember, I used the addition rule for significant figures. The least precise number is precise to the thousandth place, so the answer is expressed to the thousandth place. Once I have a molar mass, I can assemble a unit conversion factor from grams to moles. 0.0652 grams multiplied by that conversion factor times 1 mole over 195.910 grams gives 3.35 times 10 to the negative 4 units of grams have canceled, and we are left with units of moles. Here we have solutions to the other two. Molar mass of magnesium bromide is a magnesium mass and 2 bromine masses. Record that to the thousandth place, as all these numbers are precise to the thousandth place. Then the mass is multiplied by the unit conversion factor, 1 mole over 184.113 grams, to give 6.25 times 10 to the negative 4 moles. 39.1 grams of SO2. One proceeds in the same way. Calculate the molar mass, which in this case is sulfur and 2 oxygen masses, gives 64.066 grams per mole. Multiply 39.1 grams by this unit conversion factor. Cancel the grams, and the answer is 0.610 moles. Naturally, if you can build a unit conversion factor to convert from grams to moles, you can also build one to convert from moles to grams. So here are 3 compounds. You are given moles of each one. Try to make a calculation to determine grams of each. Stop the presentation, try the calculation, think about it a while before moving on and comparing your answers to the correct solutions. .3 moles of ammonium sulfate is fairly straightforward. Find the molar mass of 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens. Add those together. Record the answer to the hundredth place. And now we have a unit conversion factor, 1 mole of this this compound is 132.141 grams. So 10.3 moles can be multiplied by a unit conversion factor. Now note the conversion. Here we have 132.14 grams in the numerator and moles in the denominator. Moles cancel into 3 sig figs. We have 1,320 grams. .28 millimoles of HNO3 mean, again, molar masses relate moles and grams, so it's necessary to convert millimoles to moles. That's a fairly straightforward conversion. 10 to the negative 3rd moles per 1 millimole. We get 0.028 moles. Molar mass of HNO3 is a hydrogen mass, a nitrogen mass, and 3 oxygen masses all added together, or 63.0128 grams per mole. We then multiply the number of moles by the unit conversion factor, grams in the numerator, moles in the denominator. The solution is 1.8 grams. Name of this compound is manganese 4 oxide. We have 0.429 moles of it. Molar masses of manganese mass and 2 oxygen masses were 86.937 grams per mole. Multiplying 0.429 moles by 86.937 grams over 1 mole gives 37.3 grams. Alright, last problem for this lecture. Benzene is a component of gasolines, and it has chemical formula C6H6. So benzene's a molecular compound, obviously. How many benzene molecules are in 45.88 grams of benzene? Question again is how many benzene molecules, not moles. How many carbon atoms are in 45.88 grams of benzene? Give you a hint before you attempt the problem. The first thing to do is to convert the grams of benzene to the moles. Molar mass of this compound is 78.113 grams per mole. To find the number of molecules, we start with the number of grams, multiply by a conversion factor to convert to grams per mole. All right, so this times this is moles of benzene. If we have moles of benzene, remember that a mole of whatever we're counting is 6.022 times 10 to the 23rd. So, with this, I can convert from moles to molecules. Okay, so again, start with grams, convert from grams to moles with this conversion factor, convert from moles to molecules with this factor, and there are 3.537 times 10 to the 23rd benzene molecules. Now every benzene molecule has 6 carbon atoms, so the total number of carbon atoms is just 6 times that, or 2.122 times 10 to the 24th atoms. Alright, this concludes the first lecture for Text Unit 3.